Okay, so this is lecture 10 actually, right? Let me make. So we were looking at certain initial codecs that were invented by people. So this is our system, and we want to look at encoding, decoding techniques. So our codec, especially DNA storage codec. So as per this table, we already talked about Church, Goldman. So today I'm going to look at the third paper by Gross, which appeared in 2015. And you can see that the information density is around 1.14. Of course, it was the initial days, 2015, so it was kind of starting days. Uh, Gross used Reed-Solomon code, which is very important for data storage, for your flash drive, DVD, CD, hard disk, and a lot of applications, of Reed-Solomon codes, including your QR code that you use every day. So I'll give you some brief idea about Reed-Solomon code so that you understand what are the Reed-Solomon codes, and then you can build these systems. So in 1960, actually, this is also at the same time, uh, there was another code discovered, which is BCH code. And initially, so the method, I mean, this paper was written by Reed and Solomon, polynomial codes over certain finite fields. Beautiful paper, because I will show you how they thought. It's the original idea I am going to tell you, which is there in this paper. But these days, of course, people just talk about generator polynomial GX of the Reed-Solomon code, and they can construct the code, right? So they don't look at this basic machinery, how it was thought initially. So I always go by original idea. So I will actually tell you about this code, how they constructed initial ideas. In fact, if you want to know more about these codes, this book is available in our library, Reed Solomon Codes and Their Applications by Stephen Weicker and Vijay Bhargava. So it's kind of edited book. Interesting stuff is given about diverse applications, right from space communication till hardest actually it's revolutionized. The storage, mass media storage, flash drive, they're revolutionized by Reed Solomon codes. So they are very, very popular codes. Okay. So normally, there is a data stream. So as you know that, so Reed Solomon code actually are over a finite field, which is more than two. So so ternary, quaternary, or whatever field with q number of elements. Okay. So that is number one thing to note. So now normally there is a bit stream. You split into characters, and or maybe then one way is obviously, I mean, this is the general technique. You look at the byte strings. Byte strings are, each byte is 8 bits. Okay. So those 8 bits corresponds to an element of field with 256 number of elements. Okay. So field with 256 number of elements can be constructed using a ground field and a polynomial of degree 8. Okay. So you can construct that field with. So normally, when we apply Reed-Solomon code, we use 256 because that is the size. So basically the data string is there. You divide into this certain blocks. Okay. So K comes from there. So message blocks, and then these message blocks are converted into polynomials. So let me explain to you in general how these things are done. So we suppose we are working over a field with q number of elements. Okay. And our message bits are M0, M1, M2, Mk minus 1. So as I mentioned, so we have the data stream, the byte string, you chop it into blocks of size k. Okay. Blocks of size k. Okay. So normally, so here obviously q is 256, but I'm giving you the general method, for any q. Okay. So all these blocks, when we take a block of size k, that is our message bits. Okay. So I am saying that M0, M1, M2, Mk minus 1 are our message bits. Okay. Now what we do, I form a polynomial p of x as M0 plus M1x plus M2x square plus dot 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 Mk minus 1 x raised to power k minus 1. So this is our polynomial. So take message bit and form this kind of polynomial. I mean, so this is something where you see earlier also I have shown you this polynomial business of cyclic codes, right? Was very beautiful, right? Cyclic codes were quite easy to handle in terms of polynomials. Here also polynomials are going to play a very important role. So I take the message bits, I form this polynomial. Then what we do? So a Reed-Solomon code word, I will say that Reed-Solomon code RS, consisting of all code words of the form C is equal to C0, C1, CQ minus 1, where Ci, I can call it as again P of 0, P of alpha, P of alpha square, dot dot dot, P of alpha raised to power Q minus 1. So essentially, what we are saying, Ci is alpha raised to is P of alpha raised to power I, right? Actually, the first one, so C1 is alpha raised to power 1, and obviously with C0 is equal to P of 0, right? This is what it is. See what we are doing? A code word, we'll call it, is a member of Reed-Solomon code. Each component is evaluated at certain point. So what are these alpha i's? Alpha i's are elements of the finite field. So our field GFQ is nothing but 0. Okay. All that 1 alpha square alpha raised to power q minus 1, right? How much is there? 1 is missing here, right? I mean, this is q minus 2 actually, right? If 0 and 1 should be there actually in the field, right? So basically, out of this, we are evaluating at certain points. Out of this, we are evaluating at certain points of the finite field, right? So what we are doing, we are evaluating it at P0, P alpha square, P alpha raised to power q minus 1. So 1 we are not evaluating, right? From this point, I'm not. In fact, you can take any random, you can take certain sets out of it. I show you how it works, right? So this is our field with q number of elements, right? So basically, we are taking these points, right? Alpha So size of C. Now you know that these MIs belongs to Z2, right? So how many possibilities are there? We know that size of C, size of Reed-Solomon code will be Q raised to power K. One can show that Reed-Solomon codes are linear codes. I am not giving the proofs, but and also that dimension of Reed-Solomon code is K. Okay. Without proof, I am mentioning these facts. And length is what? Q. Length of this code is Q because they are Q. So C0, C1 up to CQ minus 1. So length is Q, right? N is equal to Q. Length of each code word is Q here. Now, let us evaluate these points and see what we are getting actually. So P0 is M0. P alpha is equal to M1 alpha plus MK minus 1 alpha raised to power K minus 1. P alpha square is equal to 0 plus M1 alpha square MK minus 1 alpha raised to power 2 times K minus 1 and so on. P of alpha raised to power Q minus 1 M0 plus M1 alpha raised to power Q minus 1 MK minus 1 alpha raised to power K minus 1 Q minus 1. So what we are doing actually, should write it down again. P of alpha raised to power Q minus 1 is equal to M0 plus M1 alpha raised to power Q minus 1 dot MK minus 1 alpha raised to power K minus 1 Q minus 1. Okay. I'm just substituting the values. Px is a polynomial. I'm just placing the values, right? 0, alpha, alpha square, and we get these. So how many equations are there? So we are getting system of equations, right? How many equations are there? Q. Q equations are there, right? And there are obviously, we can say that message bits are there, K message bits, right? Okay. Now, there is one very beautiful matrix. I don't know whether I have given this matrix to you in discrete math class, but known as Vandermonde matrix. I'll talk about it in a minute. What I'm going to do, I take out of these Q equations, any K equations, out of these Q equations. So this will be a kind of a system of equation of what? K by K, right? K MIs are there, K by K, right? So we will get something like this. Any K of these equations will give a system something like this. 1, 0, 0, 0, 1 alpha, alpha square, alpha raised to power K minus 1, so on. 1 alpha raised to power K minus 1, alpha raised to power 2 times K minus 1. One E0 alpha E alpha raised to power K minus 1. I have taken any K. There were Q equations, I have taken any k, right? Something like this will happen, right? Now, this kind of matrix is known as van der Waals matrix. So what is the van der Waals matrix? And actually, because of the van der Waals matrix, let me show you the picture of that. So I give you an exercise. In fact, I will show you first before giving you the exercise. Look at this. The matrix of this form, lambda 1, lambda 2, lambda 3, lambda n, and their squares. You take certain values. So lambda i's are distinct non-zero elements of the finite field GFQ. Lambda i's are non-zero distinct elements of the finite field with q number of elements, right? You can take alpha, alpha square, alpha cube, whatever. Distinct होने चाहिए, right? And then you square them, then you cube them, and so on, raised to the power n. Get an n by n matrix, right? Where lambda i's belong to GFQ. As long as these lambda i's are distinct and non-zero elements, all these columns of this matrix are linearly independent. Means if you take scalar multiples of them, take linear combination equal to 0, all the scalars will turn out to be 0. In other words, this matrix is non-singular. You can prove it. So this is an easy exercise for you, just to show that this van der Waals matrix is a non-singular matrix as long as lambda i's are distinct. If you see, if suppose lambda 1 is equal to lambda 2, what will happen? These two columns will be same. So determinant will be 0 anyway, right? So actually, I mean, one way of observing this, you take the first two columns, subtract first column from the second column. Lambda 1 minus lambda 2 will be as a factor you can take out. Similarly, second column and third column you do. So you will get lambda 2 minus lambda 3 and so on. So essentially, you will see that the whole overall determinant will be something lambda I minus lambda j, the product of these kind of expressions, right? So as long as lambda I is different from lambda j, right, it will be a non-singular matrix, right? Because the product looks like this. So I think still I am just giving you the hint why this matrix will be non-singular, but you can just work out. Okay, easy exercise for you. Okay, so all you need to do is just subtract this column and this column, and take lambda 1 minus lambda 2 out, this minus this, and so on, right? And then you just expand the determinant. You will see that rest of the things will be there, but essentially it depends on these lambda i's, so difference of lambda i's. Okay, so as long as lambda i's are distinct, this is a non-singular matrix. All columns are linearly independent. This is n by n. Now, what lambda I should I choose so that I can get the matrix that I am using at our place now? Actually, you can see that at our place, also it is something like this, you see. Alpha square, alpha raised to power k minus 1, then, then powers and so on. Finally, alpha raised to power k minus 1, right? Similar kind of expression is there. So this is again second exercise. What lambda I should I put in that expression so that I get this matrix? Okay. So because of this van der Waals structure, I can say that this is a non-singular matrix. Okay. This is a non-singular matrix. That means you can actually solve for these MIs. If these MIs are unknown, you can solve for it. Right? It's a non-singular matrix, right? Solution exists, right? So this is a non-singular matrix. Okay. So system has a unique solution. So basically, I want to show you that. So length of this code is Q, right? And obviously, dimension is K. Distance we can determine for this code, okay, for the read Solomon code. So what we have done till now, take the message bits and forming this kind of business, right? So code word is something like this, so that you evaluate them over these points. I can take some other points also. I'm just taking these points. This is how originally the paper was is written in the paper, right? Now there are different versions. People have, for example, construct. Normally they take Reed-Solomon code of length q minus 1. I'm constructing, giving you a construction for length is equal to q. Okay, so those kind of variations are there, but they are almost follow the similar trick. Okay, you see the beautiful idea that you take the polynomial and evaluate at certain points is a beautiful way, right, to construct the matrix. Now, how many errors it can correct? The question is, how many errors? So T, how many errors it can correct? How to find that value? I'll give you some brief argument, okay? And in fact, I will leave the details up to you. That what I am going to do now, out of these equations, so there are Q equations, right? And from this, if I choose any K equations from this, then we get something like this, right? Which is non-singular. Now, suppose that T of the code word coordinates are corrupted. So what we are saying, suppose T errors occurred. Okay, T bits are corrupted. The length is Q. Out of that, Q bits are corrupted. Okay, sorry, so length is Q. Out of this, out of that, T bits are corrupted. Okay, T bits are corrupted. So now, so once those T bits are corrupted, this will result in incorrect system here also, right? I mean, this expression will be incorrupted or it will be corrupted, right? So it will not give you proper things. Similarly, this expression, I mean, this will also will not give you proper thing because there are certain bits are corrupted when you, right? So basically certain MIs, so M0, M1, MK minus 1, K bits were there, right? So now overall code words were there. So M0, M1, MK minus 1 is mapped to C0, C1, CQ minus 1, right? That is a code word, right? Now, out of those Q bits, T bits are corrupted. So this equation will also have a problem, right? We will not be able to solve. So basically what we can compute here. So we don't know, assuming that we don't know where the errors are, right? So we might construct all possible distinct system of K equations. So out of these Q equations, I have shown you, I have taken one set of K equations, right? So basically what I'm saying that now if T bits are corrupted, I can take any out of Q equations, I can take any K equation. So how many choices are there? Q choose K. Such possibilities are there. Q choose K, right? So there are Q choose K. So there are Q choose K such systems. Okay. Q equations, and then I can choose any K. Q choose K systems. And you also observe, I'm leaving this for your imagination, that T plus K minus 1 choose K of this will give incorrect solution. Why? I think I leave it as an I mean, see, I can ask these things in the exam, so I'm just purposefully giving this small thing out of these. So Q choose K equations, right? T plus K minus 1 choose K of this will give you incorrect solution. These many will give you incorrect because there are T which are corrupted, right? So why there are T plus K minus 1 choose K of this will give you incorrect solution. Now, we can correct the errors by doing the majority decoding, right? So majority opinion among all the solutions. So we will get correct information. So majority opinion will give that as long as, so we will be able to correct the expression as long as this value is less than q minus t choose k. I mean, if and only if t plus k minus 1 less than q minus t, if and only if 2t is less than q minus k plus 1, if and only if t is equal to q minus k plus 1 by 2. So again I have not given you the reason why. So I ask you why. So what I am saying that there are q choose k such systems and t plus k minus 1 choose k of this will give incorrect information symbols. So if you use majority opinion among the solutions to all possible linear systems, we will get correct information as long as we will get correct information as long as this quantity is less than q minus 2 choose k. Okay. And so this gives us t. So we know the value of t. So in general, Reed-Solomon code has this property that n comma k comma n minus k plus 1 is the distance. Actually using certain, I mean, obviously once t is known, you can find out the value of d. Once t is known, right? So here n is equal to k, q, so you can substitute. I mean, this is a general parameter. These codes are also known as MDS codes, maximum distance separable codes. Okay. Anyway, this was the original trick to construct these codes, but we no longer construct like this. We construct like cyclic codes. So I'll just give you definition of the cyclic code, and later on I will explain how to construct those polynomials when I'll talk about BCH code. Hamming code is a cyclic code, and there is a way to generalize Hamming code into BCH code. And from the and Reed-Solomon code turns out to be a special case of BCH code. So we no longer require this kind of construction. We can directly construct using generator polynomial. So I'll just mention to you, what is the definition. So if mx is your this code word cx is mx into gx, where gx is a generator polynomial. So it is generated by gx. Gx is partial product j is equal to 1 to 2t x minus alpha raised to power j. Okay. In this case, it turns out that n is equal to q minus 1. This is a different construction. I mean, here n is equal to q minus 1. In the previous construction, we have looked at n is equal to, right? So let me show you some examples. I think that way you will understand it better. Okay. What is alpha? Alpha is a primitive element. Okay. Remember primitive element? Last class I talked about primitive element. Given a field, there are primitive elements of order. The order of the elements is q minus 1. If the field has q number of elements, order of primitive element is q minus 1. And what is primitive polynomial? A polynomial having primitive elements as roots are known as primitive polynomial. Okay. That we have talked about last time. So now I think I will use this technique here to show you. Later on, I will show you why this actually, that I will talk about it in the next class. But I'll assume that the generator polynomial is something like this. So alpha is the primitive element and T is the error correcting capability. So why these codes are very useful? T is in your hand. As an engineer, you want to correct certain number of errors. Suppose you want to correct t is equal to 10. 10 errors you want to correct. You can take powers x minus alpha square up to x raised to power x minus alpha raised to power 20, and you are done. Take alpha as a primitive element and just compute this gx, and then you start your generator polynomial is given to you. Then you can find the generator matrix and everything. You can do the cyclic code business automatically, right? So, as an engineer, these are very engineer-friendly codes. You know, in other codes, you don't have this flexibility, right? So here, gx can be constructed based on the choice of t. How many errors you want to correct? Okay, this is something very important. Let me show you some examples first. So if you take G of 8, field with 8 number of elements, you remember this is a xu plus x plus 1 is a primitive polynomial there, right? Last time we showed to you. So now, here, if t is equal to 2, if I want to construct a code which can correct 2 errors, so what I'm going to do, generator polynomial will be x minus alpha square, x minus alpha cube, x minus alpha raised to power 4. Right? X minus alpha raised to power j. J is equal to 1 to 2t, right? Product. I can expand. And then you compute, simplify, you get the generator polynomial. Generator polynomial, you can get the pair tree check matrix, and everything is done. I have not given you the clue how to decode. Actually, decoding of these codes requires solving certain system of equations. And the popular algorithm is Berlicam-Massey algorithm for decoding these Reed-Solomon codes, which sometime we can cover. Okay. So this will give you 7 is the length, q minus 1, q is 8, k is equal to 3 here. Okay, and distance is 5. Because 2 is there, right? So distance will be 2t plus 1, right? 2 into 2 plus 1. Right, that's the previous thing, right? So you can get this code. Similarly, another example. If G filled with 64 number of elements, n is equal to q minus 1. 64 minus 1 is what? 63. Alpha is the root of the primitive polynomial. We pick up a primitive polynomial there over this field, x raised to power 6 plus x plus 1. And gx is up to x minus alpha raised to power 6, because t is 3. 2t goes up to alpha raised to power 6. Simplify this, and this will give you 63, 57, 7 Reed-Solomon code. So as an exercise, I want to construct a Reed-Solomon code over 256 number of elements. So q is equal to 256. What are the parameters of the Reed-Solomon code? Q is equal to 256. So length will be q minus 1, 255, right? Then t depends on you how many errors you want to correct, right? So suppose you want to correct 5 errors, so you can do all these calculations, you know. Something very interesting, you know, so you have to do the calculations. Now, how to find these primitive polynomials and so on. I told you about the cyclotomic cosets, all that business last time, if you remember. Cyclotomic cosets, then you find out the primitive elements, multiply the primitive elements, you get the primitive polynomial, right? This machinery is very important, beautiful. This is the beauty of mathematics, right? You can actually do all those things, and you can come up with encoding, decoding techniques anyway. So this code has these many code words, and 64 is for 63, these many total vectors. So in the sphere volume, you can use something like this. Another very simple example I will show you, a smaller field actually. Suppose q is equal to 7, n is equal to 6. So Reed-Solomon code can be constructed over any field. Okay, so what here I am going to do, in G of 7, first find primitive elements. So phi of 6 is equal to 2. So there are 2 primitive elements, right? In integer modulo 7, right, if you remember. So now 3 is one of them. 3 raised to power 1 is 3, 3 square is 2, 3 cube is 6, 4, 5, 1. So ultimately 3 is a primitive element, right? So now gx could be x minus 3 to the power 1, 3 square, 3 cube, 3 raised to power 4. So now 2t is 4. So t should be 2t is 4, right? So t is 2. So distance is 5, right? D is at least 2t plus 1. T is equal to greatest integer d minus 1 by 2. If d is the distance, right? Those relationship you should know. So by taking this polynomial, I will get a Reed-Solomon code of the parameter 625. This is a Reed-Solomon code or not? How do you verify? Length is 6, k is 2, and distance is 5. Remember the distance is n minus k plus 1 minus k. 6 minus 2, which is 4, plus 1 is 5. Okay, this relationship is true for the Reed-Solomon code. So that's why this is a very beautiful code, right? Same thing, for any of these parameters, you can see that this relationship is there. Okay. So once you know D, you can find out K also, right? Because D is equal to n minus K plus 1. Okay. So you see another one, if you take this power, 2, 3, 4, 5, get something like this. This also gives you this code. You can take different powers of alpha actually. This is something beautiful, One can take any group of consecutive roots, 3 raised to power 1, 3 square, 3 cube. Give you 634. If you take this power, you get another 634. And actually, this polynomial is self-reciprocal. If you remember, I talked about self-reciprocal polynomial last time. Similarly, you take some other powers, you get another Reed-Solomon code. Right. So basically, construction of Reed-Solomon code depends on these GX and alpha and primitive. So primitive element, primitive polynomial. Right. Primitive polynomial is a polynomial which has roots. Its root as primitive elements. What are the primitive elements? Primitive elements in a finite field is all those elements which has order q minus 1. Right. So that you need to keep in mind, right? So if as an engineer somebody asks you to construct a Reed-Solomon code, so give me a Reed-Solomon code which can correct 7 errors, right? And then the person tells you the length. Rest of things you can find it out, right? Because length you know. So length is q minus 1. Obviously the ground field you need to choose, right? If suppose ground field is given, suppose normally people take q is equal to 256, right? So length is 255 and you can do all the calculations, right? Got it? This is the way to construct. So I gave you the original idea how they did the analysis. Later on, immediately, because BCH code was discovered as a generalization of the Hamming code, and it turns out that Reed-Solomon codes are a special case of BCH code. So in some day, I will talk about BCH code construction and how they are cyclic codes. Okay, so that will give you a flavor how to get this generator polynomial business. Okay, now this idea of Reed-Solomon code was used by Robert Grass in his paper in 2015. So what they have done, they've used two Reed-Solomon codes, outer coding, inner coding. So they have data source, outer coding, inner coding, DNA coding, of course, and the rest of the thing and decoding. So they had information bits of 117, and then there are adapter bits, again in the form of ACGT. Now length of chunk is 158. Number of chunks are this. They've used 83 kilobytes of data. They've encoded into this process. Let me show you the algorithm, Gross algorithm. So what they are going to do, we are going to use two kind of Reed-Solomon codes. Okay, so let me show you in details how they. Suppose we have a DAICT. For the, you have any data, right? Doc file, PDF file, whatever, right? And what you do, you have the byte strings, right? So now take two characters, so 2 bytes, 2 bytes. So for example, I have taken D and A. They both will have ASCII values, right? ASCII value means elements of the, 256, right? Those ASCII values. Then you convert them using conversion of the base. Take 2 bytes, which are actually members of field with 8 number of elements, right? Sorry, 256 number of elements. All these bytes are over 256, right? So from 256 square, because we are taking two characters, 256 into 256 square. Every 2 character is mapped to 3 characters in field with 47 number of elements. G of 47 raised to power 3. So we'll get 31, 43, 33 for II 42, 21, 35, CT 24, 45, 26 like this. 2 characters is converted into 3 characters in the field with 47 number of elements, right? By conversion, base conversion. That's all, nothing more than that. So we have this. Now what we do? So the data stream is coming, the doc file, a PDF file, whatever. You chop, you do this 2 characters, 2 characters, 2 characters, and convert it into these 3 characters over field with 47 number of elements. Now you make blocks. One block of size 594 into 30. See that 31, 43, 33, 42, 21, 35, like that. I mean, you can actually, they are written just like that. But what I'm saying that all these things are arranged in a block where number of bits are 594 here. And once, so basically you are arranging the whole data in the form of an array. Whole data stream in the form of array. One array, second array, third array, and there are how many arrays? That depends on what is the size of the data. So depending on the size of the data, so capital B depends on how many arrays will be there, right? So basically the entire information I am arranging in the form of arrays, right? One array, and each array has size 594 into 30. 594 into 30, another 594. These are the slices, right? The whole data stream is written in the form of these arrays. Now what you do? Now we are going to do outer coding. So so what we are doing basically, if you look at this vector here, this is what is the length of this vector? K bits. 594 bits are there, right? 594 bits here, 594 bits here, and so on, right? You take K bits and use a Reed-Solomon code of size, which is taking K bits and making it to 713 bits. The whole length is now, so you are adding these 119 bits extra. The whole thing, K bits are converted into N bits. That's what coding does, right? K bits are converted into N bits using Reed-Solomon code this time. So those K bits, this K bits will be converted into one row there, second row will give you another row there, third will give you another row there, right? Like that. So from this you get a block, you will get an array like this, C1, C2, C3, right? In general, typical CB. Okay, got it? So this is the outer coding by Reed-Solomon code. Understood? So Reed-Solomon code, so we are just using Reed-Solomon code right now. So 594 bits are encoded into 713 bits. K, N. So we know what is K and what is N of the Reed-Solomon code. So we know the distance also, right? Now, once we have this block CB, what we are going to do now? I'm adding certain more L bits actually from the field 40 with 47 number of elements. So here actually L is equal to 3 is shown here. So these are your CB, CB which was coming, and in this each frame we are adding these 3 bits here, right? So basically for each column, this is the column identifier, indexing of the columns actually. Okay, so we get something like this. So each vector here, MB1 is this vector, MB2 is this vector, and so on, right? Now, so basically the size of this column is L plus, so size is actually L plus M, because you see this was M, right? In the previous, this is L plus M. Now what we do, we again use Reed-Solomon code, add 6 more bits, N minus K. So this capital K I am taking as an input, and now I am using a Reed-Solomon code, capital N, comma, capital K. So taking capital K bits and converting into capital N bits. Capital K bits, L plus M, small l plus m, right? So this we are actually adding these more things, here. So we get these vectors, CB1, CB2. So each MBI will give you these kind of vectors, right? Not complex. So much complexity, right? Now what? He also wanted to protect non-homopolymer. So bits should not repeat. Do you remember there the Goldman used that table, or we have also used that table? But here what they have done, they have used a codon wheel. What is the codon wheel? You take, for example, this vector, and the bits are elements of field with 47 number of elements, right? And then all 47 number of elements are arranged on this wheel. This is known as codon wheel. How do you read? So 14 is CAG, or if you read it from here, GAC. 30 is GCG. Like that you can read. So 3 bits of ACGT. Each character of GF47 is now mapped to 3 bits of ACGT, right? And using this codon wheel, you get the DNA string, corresponding DNA string of the whole thing. One problem with this scheme is that you get homopolymers less than 3. So you may find CCC repeating 3 times or TTT repeating 3 times. So this is a drawback of this scheme actually. But still, I mean, as I mentioned to you, the in practical things, more than 3 bits should not be repeated. When we do the previous one was much better because there was no repetition at all. But here, even this kind of things are allowed. Even if 3 bits will repeat, that's okay. And they actually implemented the system, did the experiment, reconstructed the data using Reed-Solomon code. This double Reed-Solomon code business. So this coding technique was able to correct burst errors also, because Reed-Solomon codes are quite useful for correcting burst errors. So any idea? So any question? I hope you understood this. So this is 2015, such a lengthy encoding, right, scheme. Make the blocks, do this, and then they have implemented it also, right? And taken the data. But you see the experiment, they could do only for 84 kilobytes. So a question, do you think you can modify the scheme? I mean, what I'm saying that maybe you can use different Reed-Solomon code. That BTech student with the thesis which I have shown to you the last time, she have used different Reed-Solomon code. And actually there also the repetition of 3 bits was coming actually. So the good research problem is using Reed-Solomon code, can you construct the codec which will not have this repetition of ACGT at all? That is something interesting problem to look at, Can you construct that technique? Here they have used this kind of thing. I mean, this is just one way of doing it. It's not an ideal way. Okay. And I think the density was 1.14 for this scheme, which is not great, but 2 is the best one, right? If you can get 2. And I think average is 1.13 actually. So, I mean, obviously better than the average density, right? So whenever we are designing a codex, I mean, we want to have best density, right? In net density should be close to 2. And no homopolymer thing. That is very, very important. Apart from that, we can also have secondary structure free. There are a couple of other constraints. If you can do that, that will be really nice. So I think that's all for this. Thank you very much.